All right, so today we are going to be talking about joint distributions. So there is a very significant typo in the book. It will be remedied in the next email I send out to you. So most things in life depend on multiple objects. How many of you are econ people? Okay, in all of your econ models, you do not have things so simple that all the government has to do is determine the value of one key parameter, and then the rest of the economy is completely determined. Any change you make here affects other things, and it propagates. So we want to know how are things related to each other. And the main way we tackle stuff like this is the joint probability density function. So this is section 9.4, joint PDFs. And the idea is you want notation that is good. You want notation so you can glance down and really see what's going on. On the last problem on the exam, I talked at length in the solution key about what's a good way to note or to denote what you're doing so that you can quickly see the calculations and get a sense of what's going on. Think back to calculus. We used capital letters to denote antiderivatives of lowercase letters. You can quickly glance down and see how functions are related. So we will have variables x1, xn. The standard notation is to write variables in black. So rather than trying to just darken this for long periods of time, the notation that people typically use when they lecture is to just put horizontal lines. I'm on a lot of medication. Horizontal lines above the random variables. So that's supposed to denote a capital X as distinct from a lowercase. So capital is the random variable, lowercase is the particular random variable. The joint PDF will be f x1, xn. And you'll evaluate it at a point little x1 through little xn. And what's nice about this notation is you can quickly glance down and you can see what's playing in the game. This is going to involve the variables x1 through xn. So the question is, how do we define it? So for a nice set S, the probability that the tuple x1 through xn is in the set S will just be the integral over all pairs x1 through xn that are in S, f of x1, xn, x1, xn, dx1, dxn. Based on the amount of times I'm writing the same thing over and over again, and based on how sick I am, I really debated doing this as a PowerPoint Beamer lecture. But I was afraid that that would have me just warping through the material too fast. But you will notice we're going to be writing the same things again and again and again. This suggests the need for good notation. People will often write the product I goes from 1 to n of dxi to denote the product of all the stuff over there. All right, so this is the joint probability density function. What we can do from this is we can calculate the marginal probability density function. So if I know how the probability is assigned in this n-dimensional space, maybe I only care about the first quantity. And so what I'm going to do is I'm going to integrate out all the other values. If I only care about x1, I'll let x2 through xn go all the way from minus infinity to infinity. And what I'll be left with will be a probability distribution that will integrate to 1. Okay? So let's think about what's going on. So what can you tell me about this joint density function? What kind of properties must it have? I'm sorry? I actually can't hear at all because my ears are completely congested. So you have to speak loudly today. What do we know about this joint density function?
The total area under the curve has to be 1.
It has to integrate to 1. So integrates to 1. And what else do we know about it? I think somebody said it, but I really can't hear. What else do we know about this density function, this joint density function? What kind of values can it take on? Non-negative. So if you think about this, we have a non-negative function that integrates to 1. If I integrate out all but one variable, then what's left is going to be non-negative, and it will integrate to 1. Because when I do that final integration, it's the same as integrating the original thing over everything. So it's going to leave me with what will be a density function. So we'll say the marginal density of xi is f of xi, and this is where there's the typo in the book. It'll be the integral over all xk's but xi from minus infinity to infinity. I take the density function f of x1, xn, x1, xn, dx1, dx I minus 1, dx I plus 1, dxn. A faster, better way of writing this would be the product k goes from 1 to n, k does not equal I, dxk. I'm basically integrating in every direction but the xi. I fix the value of xi and I say, I care about xi, I don't care about anything else. Let me just integrate out every other variable and see what's left over. All of these variables now, x1, x2, xn, everything but xi goes from minus infinity to infinity. So if I did one more integration, if I integrated from minus infinity to infinity, I would have to get 1, because I have a probability density function. And this will be clearly non-negative because I'm integrating a non-negative function. The integral of a non-negative function is non-negative. All right, so this gives me the marginal density. So if you know the joint density function, in principle, you know everything about the marginal densities. What do you think the converse question would be? So we know that if we know the joint density function, we can get the marginals. What do you think the converse question will be? So if you know the marginals, do you know the joint density function? Think of it as you get some information, and you want to use the information you get to try to get a better sense of the big picture of what's going on. So obviously, in an ideal world, you would know the joint density function. If you know the joint density function, you've got everything. Well, that might be very expensive to know. What if I just know a little bit of information? What if I know the marginals? Is that enough to know? In an incredible coincidence, there seems to be some tables here on the board, right? Fortuitous, greatly fortuitous, right? Here are two situations, probability of y, probability of x, probability of v, probability of u. And so I'm saying x takes on the value 0, 1, 2, 3, y takes on the value 0, 1, 2. V and u are very similar. If you've been reading the book, this should be very familiar. Is this a joint probability density function? Does it satisfy the two properties? Yes, everything is non-negative. And if you sum all of these numbers, it sums to 1. What these numbers here are, these are the marginals. And so the way you get a marginal is in some sense you're summing along the row here, or you're summing along the column. And if I then just sum all of these, that's equivalent to summing every single entry. Similarly, if I sum all of these. So there is another entry I could put here. What could I write? I could write 1. Nobody does this. Chalk is too precious. It's always going to be 1, right? There's no need in cluttering your table with information like that. However, it's a damn good check to make sure it sums to 1, to make sure you don't have a mistake somewhere. OK? So if I want to look at what is the probability x equals 1, well, x could be 1 because y equals 0, because y equals 1, or because y equals 2. So if I add up the three possibilities, that gives me the probability that x equals 1, irregardless of y. That's the marginal density. Similarly, I can ask, what's the probability that y equals 1? Well, I have 4 ways that could happen. It could happen with x being 0, 1, 2, or 3, and I add up all of those. If you look over here, is this also a joint probability density function? OK. So what is the big conclusion you can get from staring at these two examples? What does this tell us? Yes?
You can know the marginal density, but the
excellent. Marginals do not imply joint probability density function. Rather than doing rigorous theoretical shenanigans and whatnot, a simple example is enough to show that the marginals do not suffice to uniquely specify your joint probability density function. I have two situations here. I have the same marginals, but they are not the same joint probability density function. They're very similar. This is from flipping 5 coins. X is the number of heads in first 3 tosses. y is number heads in last 2, and we toss 5 times. Over here, u is number heads first 3, v is number heads last 2, we toss 5 times. But there's a difference in those tosses. Coins 1 and 4 are glued together. So when we're tossing the coins, 1 and 4 will always both be face up or always both be face down. OK, there's a lot of other things we can look at. One of the big concepts we have in the course is this notion of independence. When does knowledge of one random variable give you or not give you information about another? It turns out a lot of calculations are easier if the random variables are independent. Why? You can break the analysis up into lots of different things. You can break the analysis into how this behaves, how this behaves, how this behaves, and then piece it together. So one of the big themes in mathematics is you take something complicated, you take something complex, you break it down into manageable pieces, and you assemble it back at the end. Now there are some theorems and lemmas we'll see either today or tomorrow where the proofs might initially look simpler if you assume independence, but they actually don't require independence. So there are some things where you need independence, there are other things you don't. What is the big theorem we are leading up to in this course? The central limit theorem. It says the sum of independent identically distributed random variables, if they're nice, converges to being normally distributed. Do you think the independent assumption is important? Do you expect sums of non-independent random variables to converge to being normally distributed? Almost surely not in general. Maybe my random variables are x1, 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 x1. So if I do it n times, I'm just getting n times the initial value. Or maybe my values are x1, negative x1, x1, negative x1, x1, negative x1. So I'm getting lots of cancellation. So if I have dependent random variables, all bets are off. It's much more complicated to figure out what's going on in the situation of dependent random variables. But independent random variables we can handle nicely. What does it mean for two events to be independent? The probability of A intersect B is the probability of A, probability of B. In the case of discrete joint probability density functions, it's much easier to talk about what's going on. The joint probability density function of the tuple factors as the product of the product of the marginal density functions. For the case of the continuous, what will happen here? I figured we'd not make it. All right. So what will happen here? Will this work? Nope. All right. So what will happen here is, if you're independent, we have to be able to write the joint density function as a product of the individual marginals. So we get the following. x1 through xn are independent if and only if the joint density function f of x1 xn of x1 xn is the product, I goes from 1 to n, of f of xi xi. Okay? So we have independence if the joint probability density function factors as a product. As a lot of my former Calc 3 students are here, I will not ask how many people enjoyed Calc 3. I will just let you ponder how much you enjoy doing multidimensional integrals versus one-dimensional integrals. All right, so just ponder for a minute all of those calculations they gave you in Calc 3 to do. I remember when I was at Princeton, we forced the students to take 2 cylinders and they intersected at right angles, and they had to calculate the volume in between. And at the end of the semester, I asked the students, how many of you enjoyed this problem? And not one student liked it. And I asked, should we do the problem next year? And what do you think the students at Princeton said? Yes. Why did they say yes? Because they had to do that. And that's when I told them I actually had this conversation the year before with the students who had taken the class. And that's why you got to do it. And so the cycle continues. Think about the integration you're going to have to do here. Right, as you're integrating over sets, it's much nicer if you can split this into a product of one-dimensional integrals. If things are independent, then you can split the integral, as long as your set S is nice. Okay? So this gives you an idea of what kind of sets you want to study and why we want to have independence. Okay? do you think the random variables here are independent? So if they're independent, then the probability that x equals 2 and y equals 1 should be the product of the probability that x equals 2 and y equals 1. So does 2/4 times 3/8 equal 6/32? Yes. Okay, now all we have to do is check the remaining 11 things, I think. Okay, so in principle, is it hard to just check for finitely many options? No, you just plug through and go through it. Do we need to check? No. If you look at what's going on here, x is the number of heads in the first 3 tosses, y is the number of heads in the last 2 tosses. So in this situation, by construction, they've been forced to be independent. We can actually write down the joint probability density function in this case. So for the xy example, the probability that xy equals mn. So what would that mean to be equal to mm? It means that x equals m, so I have m tosses in the first 3, and I have m heads in the first 3, and n heads in the last 2. So I've got to choose, of the first 3 tosses, m have to be heads. What's the probability that that happens with a fair coin? So I've got to have m heads and 3 minus m tails. What's the probability that happens with 3 tosses?
1/5 to the m times.
Yeah, so it's 1/2 to the m, 1/2 to the 3 minus m. But this is where it's really nice that it's a fair coin. 1/2 to the m and 1/2 to the 3 minus m just becomes 1/2 cubed. Now we need to figure out the other one. So now of the last 2 tosses, we need n of them to be heads. And that will similarly be 1/2 squared. Is this the joint probability density function? Or am I missing something?
Didn't you specify discrete?
I'm sorry?
Or isn't it discrete, right? So
Okay, so I should just say m and n are integers. So if I write m and n are integers, am I off the hook? Okay, what do I have to be very careful about? So if I take m equals -5 and n equals -12, then the probability, so what should I say about m and n? Non-negative. Well, okay, yes, non-negative. But more than that, 0 less than equal to m less than equal to 3, 0 less than equal to n less than equal to 2. And frequently, you would have a split definition. You would say it's 0 otherwise. Now, the interesting thing is, what do you think 3 choose -2 would be? How many ways are there to choose -2 people from 3? 0. There's actually an expanded version of the binomial coefficients that when you put in a negative number below, it actually becomes 0. And one of the reasons we do this is it allows us to actually be a little bit careless here. It's better not to be careless. It's better whenever you have an expression to clearly write down, when can I use this? I will not ask how many of you remember the Berlin Wall coming down. I think this is before your time. I won't ask how many of you remember a good Star Trek movie or a good Star Wars movie, again, before your time. Hopefully you remember the financial crisis. Okay? If you're in econ and you don't remember the financial crisis, this is bad. Not bad for this class, but bad for other things. Okay? One of the big problems that led to the financial crisis is people had formulas that they were using on Wall Street, and they were using the formulas without checking to see if the conditions were met. And they were assuming a lot of independence between various sectors of the economy that were highly dependent. And you got into this ridiculous situation where the more bad things you bundled together, the less risky it became, according to some of the metrics, and the higher rating you could get on your product. And there's a real danger in using equations, formulas, expressions without checking to see if it's allowed, if it's valid. When you write something like this down, and I'm deliberately doing this in a small amount of space, because this is what frequently happens. oh, I don't have that much space. Let me just quickly, I've got enough space here to do the lecture. I don't really want to erase this. I want to keep this up here, and I want to keep this up here. So I'll just do it over here. And you forget something. And then later when you come back, you then forget that there are other conditions. What you should do is you should say, I'll come all the way down here, and I'll write f of xy of mn equals 3 to the m, I'm sorry, 3, choose m, 1/2 to the m, 2 choose n, 1/2 to the n, 0 less than equal to m, less than equal to 3, 0 less than equal to n, less than equal to 2, and 0 otherwise. All right, that's a much better way to do it. Okay? Make sure you have plenty of space. Don't try to squeeze something in here. And again, you might remember it, but if someone is looking at what you're doing later on, they might miss it and they might misapply it. Okay, so lots of good stuff from this example. Any other questions before we move on to something else? Okay, so again, whenever you have a new concept, it is worth taking the time and just doing a few examples. Construct the PDF tables, the JPDF tables, and just get a feel for what's going on, a feel for how you calculate the marginals. So then there's a couple of examples in the book. All right, I'm going to leave the definition on. And what I want to do now is I want to prove one of the biggest results in the subject. And again, one of my goals is to try to give you a feel for when you expect a result to hold and when you expect a result not to hold. So the mean value, the average value, if I have a bunch of different processes and I add them together, and the first process has a mean mu1, the second has a mean of mu2, the third has a mean of mu3, the fourth has a mean of mu4, what do you think the mean of the whole process should be? So the mean of a sum should be the sum of the means. That basically, they should all go together. What if they're dependent? What if I have x1 plus x1? What should the mean of that be?
It should just be the mean of x1.
Yeah, just the mean of x1
Oh,
times 2. So the mean is 2 times the mean of x1. What if I have x1 minus x1? What's the mean? 0, which is mu x1 minus mu x1. So this is giving us some hope that the mean of a sum is the sum of the means, even if there's dependence. This is what makes the concept of the mean so useful, because it holds even if there are dependencies. The next question is, what about the variance, the fluctuations? Do you expect the variance of a sum to be the sum of the variances? Okay. So mean of a sum might be sum of means. Variance of a sum is not the sum of the variances. And so again, if we take x1 plus x2 and x1 minus x2, that should be 1s. x1 and negative x1 have opposite means, but they have the same variance. They have the same fluctuations. If I just multiply through by negative 1, I'm not changing the fluctuations about the mean. So if the variance is just the sum of the variances, these two quantities have to have the same variance. We don't necessarily know what the variance of this sum is, but we definitely know what the variance of this difference is. Right? What's the variance here? 0. So the only way the variance of a sum could be the sum of the variance is if every random variable has 0 variance. Not going to happen. That means there is no fluctuation in the world. That means everything is constant. Okay? Not happening. Any physics majors here? Chem majors? All right, so in chemistry, you might take a class on thermodynamics. You're not going to take a class on thermostatics. Not interesting. If I give you a world where every quantity is fixed, the analysis is not that hard. Right? Describe what happens over time. Okay. We're not doing a class like that. We want things to vary, and we want to figure out how to control. What this tells us, this simple example, is that variances are going to be a lot harder to work with than means. And so in terms of developing a theory, we want to develop a theory around the mean more than around the variance. Unfortunately, we are going to need to use the variance. The variance measures, to some extent, how things are spread out. But the variance is not the correct quantity to use. What's the correct quantity to use? The standard deviation. So the variance of x is denoted as sigma squared of x, and then the standard deviation is sigma of x. So again, you always want to think about notation. This is really good notation, calling it sigma squared. It's coming from the second moment, and it's also indicating that this is not the fundamental quantity. The fundamental quantity is the square root. Anybody know roughly how tall the average American is? You can either amalgamate men and women, you can split, I don't care. 5'9" for men. Okay, how confident are you on the 5'9"? 5'9" plus or minus? Okay, so you would say maybe something like 5'9" plus or minus 2 inches. You would not say the average American male is 5'9" plus or minus 4 square inches. Maybe if we're talking about other parts, no. You don't use measurements like inches squared, right? We're talking about heights. What should the measurement of our fluctuations be? The measurement of our fluctuations should be in the same scale as we're measuring the height, inches. The standard deviation has the right units. The variance has the wrong units. The units of the variance are whatever you had squared. This is why the standard deviation is the more natural thing to look at. All right, so the main result we want to figure out is what can we say about the expected value of sums? What can we say about variance of sums? Bless you. How are the dependencies going to affect things? Eventually, this is going to lead us to covariances and some very painful calculations. But if things are independent, the calculations will simplify. All right, so what I want to do now is I will keep the formula for the JointPDF on the board. And here is the big theorem. All right, so theorem. x1, xn, random variables, the expected value of a1, g1 of x1 plus an, g of xn equals the expected value, do it this way, equals a1 expected value of g1 of x1 plus an, the expected value of g of xn, if all exist, i.e., the expected value of a sum is the sum of the expected values. If you had your choice, if you were doing an analysis, what would you love to assume about the x's? Independent. So if you are tasked with proving things, you want independence. If, however, you are tasked with using this to do things, you do not want an independence assumption. What would be bad about an independence assumption? I mean, it makes the proof a lot easier. Why don't we just assume that they're independent? It greatly limits, I mean, limits is not nearly enough. It greatly limits its usefulness if they have to be independent. One of the whole points of this is to allow ourselves to look at situations where we do not have independence and get nice results. So then, of course, the question is, do these all exist? There are a couple of quantities in mathematics that we are not allowed to work with. And so I'm going to assume that everything here is finite and well behaved. So who knows the quantities we're not allowed to study? So cannot study what? What are the different expressions that are off limits? 0. 0 over 0 is off limits. What else is off limits?
0 over infinity.
No, 0 over 0. Yes, yes. Infinity over 0 is off limits. 0 over infinity is very fine. Okay. What else is off limits? Infinity minus infinity. These are all verboten. You are not allowed to study these. You can attack them through some kind of limiting process. But we are not allowed to look at infinity minus infinity. For example, if I look at the limit as x goes to infinity of x squared minus x, does that equal the limit of x squared minus the limit of x? See, I'd have infinity minus infinity. The way I can interpret that is to go back to this case and see here that, OK, the x is dwarfed by the x squared. We'll write this as x times x minus 1. And we would see that in this case, this limit of infinity minus infinity is positive infinity. If I change this to a 4, it would become negative infinity. If I change this to a 2, it would become 0. As another fun one, I will do, oh, there's one that we're missing. Which one are we missing?
Infinity over infinity?
OK, we're missing infinity over infinity. OK, we're missing 2. 0 times infinity. I'm going to show to you that 0 times infinity is negative 1. OK? If you look, here's the unit circle. If you take 2 lines that are perpendicular, there's a beautiful result in algebra that says the product of their slopes is negative 1. And if you remember your trig, if you call this theta, if you call this the 90 plus theta, you can write down the coordinates of this point. This point would be cosine theta, sine theta. Add 90 to get to this point, and then take the product of their slopes, and you'll see the product of their slopes is negative 1. So the product of the slopes is negative 1, negative 1, negative 1, negative 1, negative 1. Then I get to the place where I have horizontal and vertical. What is the slope of the vertical line? Infinity. What is the slope of the horizontal line? Negative 1, negative 1, negative 1, undefined. Negative 1, negative 1, negative 1, negative 1. How would you define 0 times infinity here? In this problem, how would you define 0 times infinity? Negative 1. So depending on what's going on, you have to go through limiting processes to see what's happening. In this situation, I would define 0 times negative 1 as, 0 times infinity as negative 1. So we've got to be very careful. When we look at what's going on over here, when we look at these expressions, I want all of these expressions to be finite. Think back to the Cauchy random variable, where the Cauchy random variable does not have a mean. We need things to exist. Ideally, what you would say is throw in absolute values everywhere. And if the expected value of the absolute value is finite, go for it. All right. So the key result is the expected value of a sum is the sum of the expected values. If we have a constant, we just pull it outside. That's not so bad. The constant means we multiply everything by a fixed factor. All right. So the difficulty is showing what happens with the different things here. The easiest case is if all the x's are the same, because then my joint probability density function is just a probability density function. So I'm not going to go through that case. That case is in the book. But whenever you're doing something like this, start off simple. And then once you have that, go to something more complicated. In the interests of boredom, or trying to minimize it, I will not go through a proof of the full general case. What I will do is I will confine myself to the case of n equals 2, and the 2 g's are just the identity map. So I'll just look at x1 plus x2. Okay? I'm not going to assume independence, though. I will assume that I have some joint probability density function. Okay. So proof when we have x1, x2. So how many of you remember the big laws from calculus? Derivative of a sum is the sum of the derivatives, derivative of a product, yada, 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 all those results. All of those proofs begin the same way. How do all of those proofs begin? So when you want to prove the product rule, yes? Definition with the derivative. You start with the definition of the derivative, and then you just manipulate. It's very similar here. You start with the definition of expectation. So we want, let's let x be our new random variable. It's going to be x1 plus x2. And we want the expected value of x. That's going to be the expected value of x1 plus x2. So what I want to do is the expected value of x, by definition, the expected value of x is the integral minus infinity to infinity of x, the density function of x, dx. All right, the problem is we don't really know the density function of x. So we have to figure that out first. Well, what is the probability that x equals x? That's telling us, I want, and this is why I was trying to leave it here. So we have a joint density function. We have an f of x1, x2. I want their sum to equal a specific number. So the way that happens is I can choose anything I want for little x1. And then once I know what little x1 is, what must x2 equal? So I want the sum to be x. If I start off with the first one is x1, what does x2 have to be? I'm sorry? X minus x1. And so if you've read ahead to convolutions, you'll see that this is really a convolution, very close to a convolution. So I now integrate over all possible values of x1. And then I would get f x1, x2, x1, x2. I'm sorry, x2 is going to be x minus x2 dx1. Okay? So this will give me the probability that my sum equals x. Yes?
On the board should be x minus x1.
Yes, thank you. And so instead of writing it like this, I'm going to write this as fx of x. So this is going to be my probability density function of getting on a value of x. And now what I would do is I would then integrate this over all values of x to see that it's a density and to make sure that I would get it equals 1. All right, so now if I want to calculate the expected value, so the expected value of x is going to be the integral x goes from minus infinity to infinity of x times f x of x dx. Okay? I'm just working with the definition. How do you find the expected value of a random variable? You integrate the values times the density. And here I now have the density. I'm getting the density from the JointPDF. So I just have to do this integral. What's the most natural thing I should do now? So what should I do if I want to try to evaluate this integral? Well, if I try to integrate by parts, I'm going to need derivatives of this. Do I know anything about f sub x of x? Yeah, it's on the board right above me. I should probably pull that in here, and I have a two-dimensional integral. I have to somehow use the information I know. Do you think it would be nice if the probability density function factored and the random variables were independent? That would make a lot of the integration easier. Okay? We're going to try to avoid using that, but in an emergency, if you wanted to do that case as a warm-up, the integration will be a little bit easier. All right, so now at this point, we no longer need this stuff. We've used it. Don't need this anymore either. Okay. So now we have the expected value of x is going to be the integral x goes from minus infinity to infinity of x. Now the integral x1 goes from minus infinity to infinity of f x1, x2, x1, x minus x1, dx1 dx. So again, I love being very specific in writing down my integration. I love putting down my variables in my bounds of integration so I know which order things are going. All right. Well, if I look at what's going on, this is the same as the integral. X goes from minus infinity to infinity. All this algebra is in the book. So if you don't want to write down the algebra, I think that's a really good idea. And just try to follow what's going on. x1, x minus x1, dx1, dx. OK. So now we want to try to evaluate this integral. So again, I can just do the algebra. I don't want to just do the algebra. I want to try to give you a sense of where the algebra is coming from. What do we expect when the dust settles that this expected value should equal? At the end of the day, what are we gunning for? I'm not allowed to use that word in school, sorry. What are we aiming for? The expected value of x is supposed to be the expected value of x1 plus the expected value of x2. I somehow better find an expected value of x1 and an expected value of x2. I would love to have an x1 here. Well, I don't even have an x2 yet, so that's problematic. One thing I can do is I can change variables. I can call this an x2. And I can let x2 equal x minus x1. So x equals x1 plus x2. Oh, that looks nice, right? We're going to have an integral of a sum. The integral of a sum is the sum of the integrals. And you can begin to see where the linearity is coming from. Well, as x goes from minus infinity to infinity for any fixed x1, x2 is also going to go from minus infinity to infinity. So this becomes the integral x2 goes from minus infinity to infinity. The integral, well, actually, technically, I've got to be a little bit careful. If I'm going to do it this way, I'm fixing a value of x1, and then I'm having x2 change. So I technically need to switch the order of the integrations. That's not that bad here. I'm assuming everything exists and is finite. This is a nice rectangular region. So I switch the orders. x1 goes from minus infinity to infinity. x2 goes from minus infinity to infinity. And now x becomes x1 plus x2. F x1, x2, x1, x2, dx2, dx1. All right. When you see an integral of a sum, you should think back to your calculus rules. This should become the sum of the integrals. And now what we'll get is we'll get the integral, x1, x2 go from minus infinity to infinity. The first one will be x1, f x1, x2, x1, x2, dx2, dx1, plus, again, x1, x2 go from minus infinity to infinity, x2, f x1, x2, x1, x2, dx1, dx2. Okay, again, this is clearly why you don't want to be writing down anything right now. You want to just look at it in the book. If the densities split, this would be a really easy integral to do. If the densities split, well, fine. Let's do the integral of x2 first. If the density splits, what's the integral of x2 going to be? So it'd be integrating f x2, x2, dx2. What would that integral be? So I'm integrating a probability density function from minus infinity to infinity. What would that integral be? It would just be 1. So if the integral splits, it's just 1. And now I would then integrate x1, f of x1, x1. Well, by definition, that's the mean. So if everything splits, it's nice. It doesn't split. All right. Well, we do the x2 integral first. What does the x2 integral mean? Fix a value of x1, and then range over all possible values of x2. By definition, what is that? It's not 1. Not the mean. The mean of x would have to multiply by an x1, and we're integrating over x2. So we're integrating now. What we can do is we can pass the integration inside and say now it's x1, integrate x2 goes from minus infinity to infinity. what should that integral be? We fixed a value of x1, and then we integrate out x2. Yes? It's the marginal density. By definition, we erase this whole thing, and it becomes the marginal density of x1. Now we look at this one. Which integral do we want to do first, the x1 integral or the x2 integral? Which one do we want to do first? x1 or x2? x1. You have a 50-50 chance of being right. Why x1?
Because you have x1 over there, and you want an x2 part.
Okay, so are we talking about this integral over here?
Well, sorry. Well, you're trying to get something that looks like e x1 plus x2.
Right. Right.
Yeah.
So this piece here is now going to come and become just the mean of x1. But in this integral here, in this double integral, do we want to do x1 first or x2 first?
X1, because you can pull the x2 out of the integral.
We can pull the x2 out of the integral. And now we have the marginal of x2. Right? So it's the same calculation as before. So when you have integrals, you only have finitely many choices, fortunately, as to which order to do it. Try them all. If it's not too high of a dimension, it's not going to be that bad. So what we want to do now is we now pull the x2 out, switch the orders of integration. That's one of our main tricks. And now we go x2 goes from minus infinity to infinity of x2. And now we integrate x1 goes from minus infinity to infinity. Put this whole thing in brackets. We've switched the order. Oh, I had already written them in the wrong order. Good, that helps. Now we have here, this becomes the marginal. So we can then erase this whole thing here and replace this whole thing with the marginal of x2. Did we really need to use independence at all? No. It helps to get a sense of what's going on, but by the definition of the marginals, we can just integrate things out. This is now the expected value of x1 plus the expected value of x2. Okay. And so that finishes the proof in the case of a sum of two independent random variables. I was saying the sum of two, sorry. I wish I could take that one back. This finishes the proof in the case of the sum of two random variables. If we had three random variables, would it be hard? What would we do?
You could like group.
Excellent. Excellent. So you can prove by parentheses. For any finite sum, it's not bad. So if I now give you the expected value of x1 plus x2 plus x3, I am a huge fan of proof by grouping. Put parentheses here. Now we have the sum of two random variables, the random variable x1 plus x2 and the random variable x3. What do we know about the sum, the expectation of the sum of two random variables? It's the sum of the expectations. So now it's the expected value of x1 plus x2 plus the expected value of x3. And now we just apply that again over here, and we get the expected value of x1 plus the expected value of x2 plus the expected value of x3. And if we had 4, 5, 6, we can now prove by induction. So I know some people had trouble with proofs by induction. This is a really good one to try now, because it allows you to skip having to do a horrible, n-dimensional integral. It's painful to be writing all this stuff on the board. This is much faster to do. So this is a really good exercise. All right, so this is a good place to stop for today. So we still have a little bit more to do from section 9.5, the linearity of expectations. So we'll finish that stuff up on Wednesday. And again, on the far board is where I will be today